Welcome back to Honors Calculus. In this video, we're going to be looking at the indefinite integral. So let me just immediately get my head out of the way and start in on this. Before we can talk about the indefinite integral itself, I need to introduce you to an idea called an accumulation function. And an accumulation function is a function defined by an integral. So we're going to define some function capital F of x as the integral from some starting point A to x of, we'll call it f of u du. So notice here, our variable for the function is in the limits of integration. And we are integrating over, in this case, a u, which we sometimes refer to as a dummy variable. What does u mean? Well, it's a placeholder, so we can talk about evaluating a function at a particular point and not call that particular point x because x already has a different meaning. And the function little f in this context is often referred to as a generating function. So let's dive in and take a look at a particular function. F of x is the integral from 0 to x of 2u du. Now, the only tool we have so far for evaluating integrals is the limit definition. So we're going to pick delta x is going to be x minus 0 over some n, which is just x over n, and evaluate the limit as n goes to infinity of the sum k goes from 1 to n of our function 2u evaluated at a, which is 0, plus k times delta x, and we multiply that times delta x. I said 2 and didn't write it down, sorry about that. 2 times u, which is 0 plus our k delta x. And so simplify. Two times 0 plus k delta x times delta x is going to be 2k delta x squared. And of course, delta x is x over n. At this point, we notice that 2x and n are all constant with respect to k, so we can factor them out of the summation. So we have 2x squared over n squared times the sum. K goes from 1 to n of k. And of course, we know from our summation rules that that sum is n times n plus 1 all over 2. Once again, multiplying through here. We have 2x squared n squared plus 2x squared n all over 2n squared, and we can divide that through to get x squared plus x squared over n. And as n goes to infinity, x squared over n will go to 0, leaving us simply with x squared. As an interesting example of how this process works, in the previous example, we took the limit from 0 to x. Just to see the difference, what would happen if we took the limit from 1 to x of 2u du? And while we could evaluate this using the same limit definition of the integral that we used previously, I want to take advantage of all of the properties of limits that we've been talking about. Namely, we can split this up and call it the integral from 0 to x of 2u du minus the integral from 0 to 1 of 2u du. That's using properties a little bit differently, but we have essentially the integral from a to b of f of u du is the integral from a to c of f of u du plus the integral from c to b of f of u du. And I took a to be 0, I took b to be x, and I took c to be 1. And if we solve for this guy on the right, we get that the integral from 1 to x of f of u du is equal to the integral from 0 to x of f of u du minus the integral from 0 to 1 of f of u du. But now that we have this, we saw from the previous example that the integral from 0 to x of 2u du is x squared. So the integral from 0 to 1 of 2u du would be x squared evaluated when x is equal to 1. So that's x squared minus 1 squared, or simply x squared minus 1. And we can generalize this. I'm not going to go through the proof of the generalization, but pick any starting point, integral from a to x of 2u du. And it's always going to be x squared minus some constant that you get by evaluating from 0 to a. And we can evaluate that and get a numerical value every single time. Speaking more generally, we call this the family of solutions. All right, and this is a theorem, it should be proven, but I'm going to use that example stand in for the proof. If capital F of x is equal to the integral from a to x of f of u du, then the integral from b to x of f of u du is equal to f of x plus some c which we call the constant of integration. So if we accept that our solution is going to be somewhere in the family of solutions and don't force that we have a particular starting point in mind, then we can name this simply as the indefinite integral. The integral without limits written of f of x dx is equal to capital F of x plus c. And again, we are just implying that when we're taking the indefinite integral, we don't know what the starting point is. So when I say plus c, I mean that quite literally. There's going to be a plus c in our solution. So if I want to take the indefinite integral of the function we've been working with throughout this video, 2u, which in this case we can look at it with x, the integral of 2x, we saw that this is going to take the form of x squared plus something. We'll call that something a capital C. So the indefinite integral of 2x is x squared plus c. With that in mind, I would like you to take a look at the integral from 0 to x of x, I'm sorry, not x, u squared du. And then once you have done that, give the family of solutions to the indefinite integral of x squared. See what you can do with those two problems, and I'll see you in the next video.